Okay, so we're going to prove that the square root of 2 is not rational or irrational. So we could write it as irrational, right? That's the same word. Okay, not rational, irrational. And we're going to state it like this. We're going to say that if a number when squared equals 2, then x is not contained in the set of rational numbers. So this symbol simply means not contained, or not in, not contained, not contained. And it's saying x is not contained in this here is the set of rationals. And the first thing in order to understand what this theorem is stating is we need to have an understanding of what the set of rationals is or are. The set of rationals is the set of rationals. Okay, so the set of rational numbers, okay, they're denoted like this. It's a set. So it contains many elements, and they're essentially the set of rationals is the set of all a over b, all the divisions, such that you have a and b in the natural numbers. And this is called the set of rational numbers. Another way to think of all the rationals are anything that can be written or expressed. Same sort of idea, expressed as the division of two natural numbers. And we should see that these two definitions, right? This is anything that can be expressed, anything that can be written or expressed as the division of two natural numbers is called, let's say, is called a rational number. Okay, so it's clear what we're defining here. And again, these two definitions, right, this set Q and this here, we should see as being the same thing. So take your time, see how these two things are the same thing. Again, this set Q is A over B, such that this line here means such that A and B are natural numbers. And you should now really see what a natural number is. The set of natural numbers is this set here. So it's 1, 2, 3, 4, and so forth, off into infinity. You keep counting, also known as counting numbers. 1, 2, 3, 4, 5, 6, 7, so forth and so forth, off into infinity. And the thing that we need to really just convince ourselves of, if we're going to understand this proof, is that every single one of these numbers, right, every single natural number, is either even or not even, or not even is called odd. So 2 is even, 4 is even, 6 is even, and then 1 is odd, 3 is odd, 5 is odd, and so forth. And every number, every single natural number, is either even or not even. And that gives you every single natural number. So to prove this, we're gonna say assume otherwise. Assume that there does exist some x contained in the rationals with x squared equaling 2. Okay? Well, since x is rational now because it's in the rational number set, right? X is contained inside Q. Since x is rational, we know we can write it as the division of two natural numbers. And we want to say clearly that a and b are natural numbers. A and b, this is a comma b, are contained in the natural numbers. Now, we got to say something a little tricky. We got to say that if a and b are both even, there must exist some m and n contained in the natural numbers with the following two properties. So with what are the properties? You needed that a over b equals m over n, and at least one, it could be both, at least one, m or n is odd or not even. Now we want to convince ourselves of this statement, right? So we want to see why this is true. So let's read it again and let's understand why it's true. It's important to understand why this one's true. So if a and b are both even, I forgot this word even, don't forget this, even, okay? So even, there must exist some, if a and b are both even, there must exist some other natural numbers, m and n, with a over b equal to m over n, and at least one m or n is odd. Now, again, why is this true? Because if a and b are both even, right? So a over b, right? A is even, b is even. Then I could divide a by 2, and I get a natural number, right? And I could divide b by 2, and I'm going to get a natural number. It could be a1 over b1, right? Now, a1 might be even again, and b1 might be even again. But in that case, I could just divide by 2 again, and I'd get another two natural numbers. And I could keep doing this until I get m over n, where one of them is not even. Because you'll either eventually get to 1, which is not an even number, or you'll get to some other odd number. If it's even again, you just keep dividing by 2. So we should see how this statement is true, just from this little reasoning right here. Now, once we have that, right, let's just consider m over n. Since a over b squared is equal to 2, we have m over n squared must equal to 2, because a over b equals m over n. So, of course, if you square both sides, you get an equality, and you can say that this must equal 2. And then you can say that m squared over n squared is equal to 2 when you just, do m over n times m over n, m squared over n squared equals 2. And then when you multiply by n squared, you get the important equation. You get m squared is equal to 2n squared. So I got that by just multiplying on both sides by n squared. Because n squared divided by n squared is 1. So you get m squared, just on this side, 1 times m squared is just m squared. And then I multiplied again by n squared over here, so I get the 2 times n squared. Now, this equation, right, we want to start to look at what this equation is saying. The first thing to notice is that this is some natural number, and this is some natural number, because m and n are both natural numbers. So m and n are both somewhere in here, somewhere in this set, right? And we know, or we're saying that at least one m or n is odd, okay? That's what we have so far. So we should see that a natural number squared, this part, is another natural number. If I multiply a natural number by a natural number, I get another natural number. And if I multiply it by 2, I get another natural number. And a natural number squared is a natural number. So I have natural numbers on both sides. So that means that this number must be either even or odd, and this number must be even or odd. And of course, an even cannot equal an odd. An even cannot equal a not even. So what do we have here? On the right-hand side, right, I have 2 times some natural number. 2 times any natural number is always even. And you should just sit there and just be like, of course, 2 times any natural number will always be even. It doesn't matter what the natural number is. So we have here that this side is even, right? So then that must mean that this side is even. So this implies m squared is even. M squared is even. And if m squared is even, then m is even. And we should prove this fact here. So go from here to here, right? Maybe maybe it takes some convincing that if a number squared is even, then that means that the number is even, right? So we can prove that on the side, and we can say, okay, so let's prove just a small if any natural number squared is even, then m is even. And to prove this, we do a proof by contradiction. Assume, right? So what do we have in this one? We have that m squared is even. And we want to prove that m is even then. So assume m is odd. Assume the opposite. And we're going to get a contradiction. So assume m is odd. That means that m can be written as 2k plus 1, where k is any natural number. Now, we want to just convince ourselves that if m is odd, then m can be written like this here, where 2k plus 1 can be any odd. So what do I mean by this? So look at the odds. If it's 1, then k is 0. If it's 3, k is 1. If it's 5, k is 2. If it's 7, k is 3, and so forth. And I'll be able to get any odd with the appropriate natural number k. And k is a natural number, right? So we just need to convince ourselves that if m is odd, and if m is odd, then m can be written like this. Okay, just take your time. Now, consider m squared, which is, in this case, 2k plus 1 squared. 2k plus 1 squared, take your time, FOIL it out, is, is 4k squared plus 4k plus 1. And then this is 2k squared plus 2k plus 1. When I factor out a 2, you can check. If I distribute the 2 back, I get back the original one. So I have that m squared is equal to this. But now we should see that this here is some other natural number, whatever you want to call it L. This is some natural number, right? This is 2 times k, which is a natural number, and then plus k squared times 2 is a natural number times 2, plus 2 natural numbers added together is another natural number. So this is 2 times L plus 1. This part is even, and then plus 1 makes this odd. And we can say m squared is odd. And this is a contradiction because we're given the fact that m squared is even. And we can say assumption is false, m is even. And we're done with proving what's known as the lemma. So I just proved this implication. If m squared is even, then m must be even. So I proved this implication, this whole thing here. Now we go back and we say, okay, m is even. So if m is even, then m is equal to 2 times some natural number k. And I'll just use, k again, but it doesn't matter. I mean, 2 times k, right? Every even number can be written as 2 times k. When k is 1, then it's 2. When k is 2, then it's 4. When k is 3, it's 6, so forth. You're going to hit every single even number for the appropriate k. So every single even number can be written as 2 times k, where k is any natural number. Now, if it's the case that I could write m as 2 times k, then in this top equation, right, go back to it, I have m squared, let's write it again, is equal to 2n squared. But now, instead of writing m, I'm going to write 2k, which is 2k squared is equal to 2n squared. Then I square this out. I'm going to get 4k squared is equal to 2n squared. And now what I have here again, these are all natural numbers that I'm dealing with. K is a natural number, n is a natural number, and I have that 4k squared is equal to 2n squared. And what I can do here is that if I divide by 2 on both sides, I'm going to get 2k squared, because 4 by 2 is just 2. 2 by 2 is just 1, so I get equals n squared. Okay, and again, these are still natural numbers. I was able to divide by 2 knowing that 2 goes into 4, right? And I still have a natural number because 2 times a natural number is still a natural number. And then I get 1 here. 1 times the natural number is, of course, the same natural number. So now if I look at this equation, it's similar to what I had up there for m. And what I can say is n squared is even. Why must n squared be even? Because this side is even. This must be even. It's 2 times some natural number. So that means that this must be even. And then if n squared is even, from this logic, right here, from this logic in yellow, right, m squared is even, whatever, call it n. N squared, n must be even. So I have n is even. And now I have a contradiction because n is even and m is even. But at least one m or n must be odd. So you have the contradiction. Assumption is false. And you can say the assumption is false. What's the assumption? That there does exist. You could say assumption is false. There does not exist x contained in Q with x squared equaling 2. And now you're done.